In problem 1, we are graphing each inequality on the number line and then writing the solution set in interval notation. When graphing these inequalities, we have to be careful as to what inequality is here. You can see in part A, we have a greater than or equal to sign. In part B, we have a less than or equal to sign. Determining on whether it is greater than or less than is going to determine which side the line points to, whether it's pointing left or pointing right. Another differentiation is in problem 2, part A, where we have x is greater than 2. There's no little line underneath. That tells us if 2 is actually in the solution set or just outside the solution set. We're going to look at these 3 examples together and see how each one of these differs. Looking at part A, x is greater than or equal to -3. When we have a greater than or equal to sign, we're going to put a solid or filled in circle on the number line indicated in the inequality. Next, we have to determine if the line coming from that dot goes to the left or to the right. One of the easiest ways to do this is to just pick a number on the number line and determine, is this number truly greater than -3? I'll choose a positive 1. Is 1 greater than or equal to -3? Yes. That means I'm going to be pointing my line from -3 in the direction of -1. Now it's not going to, positive 1. It's not going to stop at positive 1. We just know that that's the direction that this line is going to head. It's going to continue on through infinity. Next, writing this in interval notation. Whenever we write a solution set in interval notation, we start with the smallest number in the solution set. In this case, the smallest solution is -3. We start with -3, and it goes all the way up forever and ever. It never stops. It's limitless. In order to notate this, we are going to use the symbol for infinity. Finally, we have to determine what kind of brackets we are going to use on the outside of this interval. On the left-hand side, -3 is included in the solution set, so we are going to use a hard or square bracket. Now it goes up forever and ever and ever. It's infinite. Now infinity is a concept, not a number, so we can't include infinity in the solution set. Therefore, we're going to use a soft bracket. With any solution set having to do with infinity or negative infinity, there will always be a soft bracket. Now in part B, x is less than or equal to -35. We have a less than or equal to sign there. We have that little dash, which means we're going to have a solid circle again. Now I'm going to pick a number at random and see if it is truly less than or equal to -35. I will choose -31. Is -31 less than or equal to -35? No. So I'm going to point my line in the opposite direction. Not going to include -31. I'm going to go towards negative infinity. Now this goes infinitely to the negatives, which means that there is no smallest number. Again, we are going to have to use the symbol of infinity, but because we're going to the left, we're going to call it negative infinity. Going all the way to the right, we go up to -35. Again, negative infinity is a concept, not a number, therefore we're using a soft bracket. We go up to -35, we have a solid circle, we use a hard bracket. So just because we haven't seen one, I'm going to do part A in problem 2 as well. X is strictly greater than 2. There's no little dash, so it's not greater than or equal to. When there's no dash, we use an open circle. Do not fill it in. X is greater than 2, so if I was to look at 4, is 4 greater than 2? Yes. So I know I want to point my line in the direction of 4, but it continues beyond 4. It goes all the way to forever and ever and ever and ever. Written in interval notation, we start with 2 because 2 is the smallest thing. However, we can't include 2, so we're going to use a soft bracket. When there's an open circle, there's always going to be a soft bracket. It goes on forever, so we put the symbol for infinity, and just like any other infinity, we will always have a soft bracket.